Out of the box, a new Kubernetes cluster is open. Every pod can talk to every other pod, and any workload can consume all available CPU and memory. Without internal boundaries, unauthorized access at one point can spread across the entire system. To fix this, we need to apply 6 specific security layers. We are going to lock down network traffic, restrict user permissions, automate compliance, and properly encrypt our secrets to build a production-ready environment. To follow along, you need 3 tools running on your machine. This terminal shows successful version checks for a local Kubernetes cluster, kubectl to interact with it, and Helm to manage our package installations. Establishing this secure baseline isolates potential problems. If one component is compromised, these layers ensure the intrusion is contained and cannot infect the rest of the cluster. We partition our cluster using namespaces, carving out isolated zones for teams like payments, shipments, and scores. Next, we attach resource quotas. This hard limit guarantees a heavy application hits a ceiling, preventing it from starving other teams of CPU or memory. With the cluster divided, we restrict what individual users and pods can actually do inside those namespaces using role-based access control, or RBAC. RBAC relies on 3 core components. First, a service account for each pod. Second, a role granting explicit permissions. Third, a role binding connecting the two. Looking at this split screen, you can see how we test these boundaries in practice. We use kubectl auth can to attempt an action using our restricted service account. When we try to delete a pod, the terminal returns a no. By combining namespaces, quotas, and RBAC, we ensure that if a pod is hijacked, its ability to interact with the broader cluster is strictly confined. Controlling permissions is step 1. Step 2 is controlling network traffic. By default, any pod can ping any other pod. We replace that with a zero-trust model, blocking communication unless explicitly allowed. If you are following along on a local kind cluster, you must install a networking plugin like Calico first. Without it, your cluster accepts network policy configurations, but won't actually enforce them. This diagram illustrates our network policy in action. A YAML manifest uses label matching to explicitly restrict incoming traffic, allowing connections only from specific front-end pods. When tested, the attacker pod's network request hangs completely, while the front-end's request resolves immediately. This chokes off lateral movement. If a bad actor manages to penetrate the front end, they are isolated in that pod. They do not get a free pass to scan the network or extract data from the back-end database. Even with strict network and access rules, human error remains a risk. A developer might deploy a pod using the latest image tag, breaking production as application versions change. To prevent this, we need automated policy enforcement. We accomplish this using an admission controller. This automated checkpoint intercepts and evaluates the configuration of every single deployment before it enters the cluster. We use Kubernetes to manage this. You install it via manifest, but you must wait until the pods are shown in a running state. If you try to deploy policies while they are still initializing, the webhook will fail. With Kubernetes running, we deploy a cluster policy resource. This policy automatically rejects any incoming pod attempting to use the latest image tag. Here is the validation in practice. When we try to deploy an Nginx container with the latest tag, Kubernetes intercepts the request. The terminal throws this exact error message, blocking the pod creation entirely. Now we need to address how Kubernetes handles sensitive data like passwords and API tokens. The default Kubernetes secret resource provides a false sense of security. The data is only base 64 encoded, not actually encrypted. This side-by-side code comparison shows the problem. Anyone with basic read access to your namespace can copy the encoded string, pipe it through a standard decode command, and instantly reveal your plaintext password. To secure this data properly, we install the External Secrets Operator, or ESO, alongside a dedicated secret manager like HashiCorp Vault. Vault safely encrypts and stores the actual credentials. Instead of putting sensitive strings in our code, we create an external secret manifest. This file contains no passwords. It only contains a reference path. ESO reads this path, authenticates with Vault, retrieves the real credential, and safely injects it into the cluster. To verify the setup, we deploy the external secret manifest and inspect the cluster. We can see that ESO has successfully communicated with Vault and generated the required secret resource on the fly. An external provider keeps credentials encrypted at rest. you can safely store configuration files in version control without exposing a single actual password. We have taken a completely open, vulnerable Kubernetes cluster and locked it down. It is now logically partitioned, firewalled, automatically compliant, and properly handling encrypted secrets. But configurations drift over time as teams push new code. You must routinely audit these specific layers to ensure your defenses remain intact. This 4-step checklist provides a framework for testing. Step 1. Run auth-cani commands to verify RBAC limitations. Step 2. Attempt cross-namespace network connections to test your firewalls. Step 3. Deliberately deploy a bad image tag to trigger Kyverno. And Step 4. Confirm all code repositories use external secret references rather than hard-coded credentials. You can find the exact YAML manifests and terminal commands to execute these auditing steps in the repository linked below. Zero Trust Kubernetes requires a continuous cycle of strict isolation, automated enforcement, and consistent validation.